Scientists use physical and chemical properties to describe and classify matter. Things like color, shape, or texture can tell us about the matter and how that matter behaves. Well, nanotechnology isn't just exciting because it's small, but also because of the new properties that emerge. This bottle contains gold nanoparticles, but it doesn't exactly look like the yellowish gold in your mom's jewelry box. The vibrant color is produced because of the way the nanoparticles interact with visible light. We can control the color produced if we change the size or shape of the gold nanoparticles. This is helpful when creating sensors, probes, and it is even being used in cancer research. In the Middle Ages, artists created beautiful stained glass with gold without even knowing they were using nanotechnology. If you could control a material's physical and chemical properties, what would you create?
Stronger than steel, more pliable than rubber, and able to conduct electricity. This amazing nanomaterial is made entirely of carbon. It's graphene. Possessing remarkable physical properties, graphene is a material of the future.
Graphene has been called a wonder material. It's one of many nanomaterials that has extraordinary properties.
Graphene is only one atom thick, so it only absorbs 2% of light that passes through. This means it's almost completely invisible. With this kind of material, it's easy to imagine a flexible cell phone or wearable technologies. Graphene is such a new material that it wasn't even discovered until 2004 by some very curious scientists with pencils and Scotch tape.
And so they put one piece of Scotch tape on the graphite, peeled it off, and you had a little piece of the pencil lead on that tape. And you took another piece of tape, literally Scotch tape, I kid you not, put it on that, peeled that off, and they got another layer on both pieces. So they kept doing that until you got down to the point where you had to look with a microscope and see what was left. And when they got down to the most reduced layer, that essentially was graphene.
See, the graphite in your pencil and graphene are both made entirely from carbon. They are allotropes, or different arrangements of carbon atoms. Even the diamond in your aunt's wedding ring is an allotrope of carbon, but a diamond is clear. Graphite is black. A diamond is strong, and graphite crumbles apart as you write. So what gives? The differences in the physical properties come from the arrangement of the atoms and the bonds between them. What other things can we create if we can control the structure of matter?
A fullerene is an allotrope of carbon. If you look at if you think of a soccer ball that is made up of hexagons and pentagons, at each one of those intersections, if you put a carbon atom, then you would have a ball, a hollow sphere, which we call a fullerene or a buckyball, and that would be a C60. So in that arrangement, there would be 60 atoms, and it would make up this hollow sphere, this ball. But there are other fullerenes of other sizes and other numbers of carbon.
So if graphene is so wonderful, why aren't we building everything out of it, like transparent computers?
A nanomaterial isn't just a nanomaterial because it's small. It's a nanomaterial because we can manipulate it at the nanoscale. That meaning I can somehow control it with my tools or processes in such a way that I can leverage a unique property. That's what makes a nanomaterial. So it isn't just miniaturization. It's hard. It's really, really hard.
Carbon nanotubes, another allotrope of carbon, are shaped like cylinders. Basically, they look like drinking straws on a nanoscale, but they have extraordinary properties. In fact, some companies mix carbon nanotubes with other materials to make a composite that is lighter weight and stronger. Now imagine if you could use that to build an airplane.
Everything that we make is dependent on materials, when you think about it. The steel that we use on our ships, the aluminum that we use on airplanes. We're interested in strength, we're interested in stiffness, we're interested in a whole host of properties to make our products more effective. If you've ever seen a bridge being built, usually they have these metal bars inside the concrete. Those are called reinforcement bar or rebar. At an atomic level, carbon nanotubes are not much different. We take carbon nanotube rebar and we're mixing in composite around it. And that's what provides the additional strength. The same way you'd want a bridge made of concrete to be absolutely solid when you're driving your cars and trucks over it. We want our composites absolutely solid for whatever structural purpose we're using them for.
Carbon nanotubes are also highly conductive. Conductivity is a physical property that measures how electricity flows through a material. What could you build if you had a material that offers lightning strike protection?
You can actually go to a lab and have them artificially generate lightning, which is pretty cool, 200,000 amps. It's a lot of power. And so we put one panel with just the carbon fiber and epoxy, and then we put one panel with carbon nanotubes embedded in the carbon fiber and epoxy. And so we struck them both 5 times in the same place. And so then the results were the panel that was not treated was clearly damaged, like dramatically damaged. And then the panel that was treated, because it had the carbon nanotubes embedded in it, which are conductive, was able to disperse the energy of the lightning strike and protect the integrity of the material. So which would you rather have on your airplane wing?
New materials offer better properties, but manufacturing can be challenging.
And these tubes are the diameter of DNA, but we make them at about the trillions per second. And then we spin them and turn them into things that look like black thread. So here's an example of what we're able to do is actually turn them into fiber, and this fiber can be turned into a rope. This is the only one ever made in the world right now. This actually has 1,000 pound breaking strength. And we have another higher strength version that has 2,500 pound breaking strength. That's actually stronger than steel. But you can't exactly do this with steel. This is electrically conductive. So here for the first time you're actually seeing this material and in a useful format. So you're taking the textile industry techniques of 100 years ago and applying them to a 21st century molecule, carbon nanotubes.
Okay, so it may be a while longer before we see graphene and carbon nanotube factories in our neighborhoods, but scientists are still investigating new ways to create advanced nanomaterials. Imagine how much further the science could take us.
Our specific materials, actually it's a sheet material, has been used on the Juno spacecraft. It's going to be a marvelous mission. I think we're going to be stunned by photos that are going to be taken by that satellite because they're almost going to fly it down to the cloud tops on Jupiter and then back out. So our materials are there to protect the critical attitude control thrusters, the engines, and the main engine so that it will work.
I deliberately call what we're in a materials revolution. Everything that we make, all our technologies are dependent on materials and our ability to leverage them. We're doing things now at the most fundamental level, controlling material properties that's different than we've ever done before. And that is going to change the kinds of things we can make, how we go about making them in the future.
Yeah, our middle school students today will be the people who will take the nanotechnology way farther. They'll be the folks who will actually make this broadly used in everyday life, where we're just scratching the surface. They'll make the entire thing happen.